Hello, everyone. This is our FEA analysis on a snowboard. My name is Tia Taisingfong, and my partner is Charles Ganu. During this presentation, we're going to be doing a recap of our selected system, principles, and diagrams, our simplified FEA model, and our FEA formulation and governing equations, and our numerical results for the FEA simulation. Just a recap of our system. We chose a snowboard, which is designed to withstand bending, torsional, and impact forces during its use while maintaining performance and safety. And the focus of our project is to analyze the stress distribution, deformation, and failure modes of the snowboard under operational loads.
Yeah, so a recap of the operational principle. Flex is the first principle, and that's just the rider pressure that the rider exerts to the forces to the edge of the snowboard, as well as the general surface area of the snowboard. Then we have torsional rigidity, and that is the bending force within the snowboard given on different impacts, whether they're landing or the general force on the lateral incline. And then we have vibration dampening, and that's applied using the wood surface as it is able to dampen or absorb the shock of impact and force. So here is a preliminary design, and this is just a recap of it. So the top sheet is just a protective layer of the snowboard. Then we have fiberglass as the second layer. The third layer is the core, which is wood. And then the layer under that is fiberglass again. And lastly, the layer to the bottom of that would just be a protective polyethylene base as well. And this just reduced the friction that the snowboard feels when it's going down different surfaces, particularly being snow. And then the fiberglass and wood are used to absorb impact of shock and dampening, and then as well as to absorb different forces and reduce rigidity.
So for our simplified FEA model, it was modeled in Inventor. The picture on the left shows the core layer of the snowboard, which is wood. The dimensions, we decided to use a 147 centimeter snowboard, and then the width of that board would be 30 centimeters with a thickness of 1 centimeter. And then the snowboard core physical properties, as I said, is a composite wood and fiberglass. For the CAD model, we decided to use cherry wood since there was no fiberglass composite material to use. For the boundary conditions used in our calculations, we have our rider weight set at 145 pounds. Lateral forces from the slope are 330.4 newtons due to the 40% gradient. The normal force is 825.97 newtons perpendicular to the surface. And then the lateral forces from a carved turn is 500 newtons, and the vertical impact from landing is 1,000 newtons.
Here are some key formulas to consider. The first one is the bending formula, and this one specifically for the Q, this is the distributed applied force on the snowboard. And then you have the D sub X, the D sub X and Y, and the D sub Y. And these are the flexural rigidities. So the different directions that the snowboard is going to bend. And then as well as along in the equation, you will have stress in the X and Y direction, as well as the stress max. And then for Y, you'll also have the vertical deflection. Second equation is shear, and the d sub xy is the shear rigidity, and then the gxy is the shear modulus, and then h would just be the thickness of the snowboard, and then we have the Poisson's ratio for the v x sub y and v y sub x. Third, we have the bending stress, and so this would be the bending max stress, and then you would have that equal to the moment of inertia as well as the bending moment. And then lastly, you would have that equal to the perpendicular distance of the neutral axis. Lastly, we have the criterion failure, Tsai-Hill failure criterion. And so that would just have to be less than or equal to 1. And if that is above 1, that would mean that the failure safety is for the structure is highly unsafe. And so that structure would essentially deteriorate or face some type of disconfiguration. And then going to our calculations that were done from these equations, we can correctly say that our failure safety is 5 times 10 to the negative 6. So that's way far below 1. So the structure is very soundly safe. And then from there, if we also talk about our bending and shear calculations for our bending or shear rigidity, it's 458 newtons per meters. And then for our bending force, that would be the maximum of that would be 10 times 10.88 kilopascals. And yeah.
So for our ANSYS simulation or the numerical results, we modeled it in ANSYS and put fixed supports at the holes for the screws where the rider's boots would attach to. And then we applied a force downward onto the middle of the board, which is the effective area of the snowboard where the rider um, does turns or jumps. And then for our maximum principal stress, we had 55,236 pounds per square foot. Um, Using the von Mises stress, we got a result of 70 or 67,718 pounds per square foot. The max shear stress was 13,199 pounds per square foot. And then the total deformation was very small, and it is 1.72 times 10 to the negative fifth pounds per square foot. And most of the stress, shear, um, and deformation, or not the deformation, but the stress and shear occurs around the hole areas where the effective area of the board is, and the total deformation is at the tail end of the board, as shown in the top right figure. Um, but this board does hold up very well under the rudder load during turning and jumping. So we went ahead and just finalized those results. Thank you for watching and listening.